Good evening, High Legh. Pleasure to be back again. This time with a slightly different slant. Rather than talking about the science of how the universe works, this is a sort of a personal take on this wonderful instrument, the 200-inch telescope, which, from the cryptic title 200 at 75, is now nominally 75 years old, or at least first light was 75 years ago. So this image was taken 1951, a few years after the 200-inch telescope was built. And I think I saw this image in a book maybe 20 years later. So sometime in the early 70s, I saw this image and I thought, is this what the universe is like? What's out there? What is that? What's it made of? How did it come to be that shape? This image, more than any other, got me interested in astronomy because I saw this in a book and I wanted to know more. So I read more books, looked at star atlases, etc. So that picture taken in 1951 got me started. So in a sense, I've got a personal connection with this image and the telescope that took it. I've taken inspiration from a number of different sources. I'll acknowledge them right at the end, but in particular one book that I read that was written in 1939 about the so-called glass giant of Palomar. And again, this got me very interested in understanding more about the history of this particular telescope, which was the largest telescope in the world when I was born and the largest telescope in the world for most of my childhood and probably half my adult life. I just love the sort of quotes that crop up in this book. Barometer up and humidity down. One of those crystal clear nights when the stars fairly crackle. Just gives you an idea of just how wonderful observing can be on the right conditions. So I'm going to say a little bit about the man, George Ellery Hale, but not much because I haven't got time to go into his life history. But he was a bit of a billionaire whisperer. He managed to get money out of people to fund the largest telescope in the world. Not once, not twice, not 3 times, but 4 times. He was instrumental in building the 40-inch, 60-inch, 100-inch, and ultimately the 200-inch. Again, I'm not going to cover all of that, but I'll give you some of the context. Regarding building the 200-inch telescope, I'll say a little bit about how they selected the site on Palomar Mountain, how they made the mirror, how they made the telescope. And I'll try and bring it a little bit up to date by saying what it's doing now. And then I'll acknowledge the sources of information I've been using. So Hale, the man, is often not realized that he made such contributions to observations of the sun, spectrohelioscope, imaging the sun at various wavelengths. That's often forgotten because a lot of people simply associate him with the fact that he has been instrumental in building the largest telescopes in the world in the last century or so. So he's always had the vision and the drive to always build bigger and build better. But it started because he simply wanted to take his techniques of looking at the spectrum of the sun. He wanted to be able to look at the spectrum of the stars as well. And in order to do that, you need to collect more light, hence the desire to go to larger and larger apertures. So he was the director of the Hlco Observatory when they built the 40-inch refractor, the largest telescope in the world. Then he moved to Mount Wilson Observatory, became the director there, and oversaw the construction of the 60-inch reflector, the largest telescope in the world at the time. And that led on to the Hooker telescope, the 100-inch Hooker, again, when it was built, the largest telescope in the world for the 3rd time. Notice that the largest telescope in the world, that moniker goes to telescopes whose apertures are getting larger, roughly speaking, by increasing the aperture half as much again. In other words, doubling the area of the collecting area of the lens or the mirror. From 40, half as much again to 60, roughly half as much again to the 100. The Hooker telescope was operational as of about 1918, but as soon as it was built, Hale said, we need something bigger. He was always thinking of the next telescope. It wasn't a question of let's wait 10 or 20 years and then build the next one. As soon as one was operational, he was thinking of the next. It took quite a while to get the money for the next telescope. Some people were thinking, well, 100-inch, half as much again is 150-inch. That would be a sensible jump. Some people were saying, why are we limited to that? Why don't we just make something huge, like a 200-inch? Other people said, well, if you're going to go for 200, why not 300? And yes, there were sensible plans on the drawing board for could we actually build a 300-inch, but It was considered infeasible with the technology of the day, but 200-inch was still an enormous change from the 100-inch. Double the diameter, 4 times the area, potentially 10 times as massive if you simply try and scale up. So it took Hale quite a while to get the money. He started in 1918 effectively, but it took him about 10 years to find the money, going to various billionaires around the world, trying to persuade them, give me enough money to build the next generation of telescope. In 1928, he approached the Rockefeller Foundation, and he somehow managed to get them to pledge $6 million to build not just the telescope, but the telescope and the dome and the entire observatory infrastructure, which didn't exist at that time. $6 million then, back in the 1920s, some fraction of $1 billion today. So persuading somebody that that was worth doing was quite an achievement. Having got the money, what's the next step? Well, the next step is deciding where you're going to build this particular telescope or observatory. Now, these days, of course, we think of the best sites in the world as being the top of a volcano like Hawaii or the Canary Islands or possibly the Atacama Desert. But at the time, Hale said, okay, they might be good places in terms of seeing, but if you want a big observatory, if you want a world-class observatory, you put it close to where you have all the infrastructure, the machine shops, the optical shops, the experts living, of course, in America. Therefore, where do you put it? You put it in America, ideally next door to where he was living. So that might seem a little bit parochial, but he did not want to build the world's largest telescope halfway around the world where he couldn't effectively keep control of the infrastructure. So he looked at what was going on in the vicinity of Los Angeles. Admittedly, a lot of astronomers were working in California, not all of them by any means, but a fair concentration of them. So there's Los Angeles, as we understand it today, the island of Catalina, just off the coast there. And Mount Wilson Observatory is in the mountains just to the north. But even back in those days, Los Angeles was expanding. We have San Fernando, San Bernardino. You can see it starting to wrap around Mount Wilson and, not surprisingly, produce an awful lot of light pollution. So it was realized that they had to find somewhere other than Mount Wilson. Couldn't go there. So he started looking at various mountains in California, sending out scouting parties to go to the top of various peaks, check out the seeing. Half a dozen different sites were found that all had excellent seeing. So how do you decide between them? Well, you take a geologist, Professor Richter. Yes, he of the Richter scale was just down the road at the neighboring university. So they asked them geologically which would be the best place to go for. And Richter said, well, I'd strike that one off your list. Why? It's on the San Andreas Fault. Not necessarily a good place to put an observatory. But there is one place on your list which has got excellent seeing, which would be advisable. Palomar Mountain. Why is that good? Because it's a chunk of granite, 30 miles long, 10 miles wide, 25 miles deep. That is quite a few trillion tons of granite. Even if California gets hit with an earthquake, that's not going to move. So that's an excellent place to put an observatory. So we've got San Diego to the south, about 60 or so miles. San Diego was fairly large even in those days, and of course has got larger. But 60 miles from San Diego and 100 miles from Los Angeles was considered far enough that light pollution was not considered too much of an issue. They weren't intending to ever observe with the telescope pointing towards the horizon, so that was considered acceptable. So Palomar Mountain was chosen. Beautiful place. That's what it looks like in the summer or the autumn. I visited it in spring of 1982. Yes, that's me with slightly longer hair. That's 40 or so years ago. No, I'm not wearing the same shirt. Okay, that's good. But yes, when you visit it on a nice day with your sleeves rolled up, you don't appreciate that at that altitude in winter, it does actually get rather cold. And yes, it gets a significant amount of snow at the altitude of 1,700 meters, or about 6,000 feet or so. So you need to employ people to shovel snow off the dome, otherwise the dome gets rather heavy with all of the snowfall. And the only way of getting up there at the top of Palomar Mountain, the only access at the time, and pretty much for years later, was this very, very windy road. That was the only way of getting anything to the top of the mountain. And remember, there was no observatory there, no infrastructure whatsoever. So it's not just a question of building a telescope and a dome. The entire observatory site had to be taken up on the back of trucks up this very, very windy road of whatever it was, 12 miles or so of a lot of twists and turns. So we've got the money, or at least we've got the pledge of $6 million. We've decided where to put it. What's the next decision that needs to be made for the world's largest telescope? We have to think about how it's going to be mounted. Now, as amateurs, we know that there's various ways that you could, in principle, mount a telescope. The German mount with a counterweight, a fork mount that doesn't need a counterweight but has a lot of strain on the polar axis, or you effectively extend the polar axis to both sides of the telescope, in which case you get a support in the north and the south, and then you get an English or a yoke mount. So those are three possibilities. I found it quite curious to realize that when you look at the three previous telescopes that took the mantle of the world's largest telescope, each of them used a different mounting. The Hlco's was the standard German mount with a large counterweight. The 60-inch was a fork mount. It doesn't perhaps look much like a fork mount because the arms are very short, because the center of gravity of this particular system is very close to the mirror, but it is a fork mounting. And the Hooker telescope was a yoke-mounted design. So he's already had experience of using each of those three designs. What are you going to do if you want to scale this up to a 20-inch mirror, which is going to be nominally 4 times the area and perhaps 8 times the mass if you simply scale it? In other words, do you want to build a telescope which is simply a scaled up version of the Hooker telescope, which has only just come online, and you're thinking, well, okay, it's just about proved itself, but do you simply want to scale up, or do you want to do something more innovative? Hale was determined that the new telescope, the 200-inch, did not suffer from the same limitations as the Hooker. And the Hooker had arguably 2 limitations that are worth talking about. It may have had a few more. But 2 of the limitations he wasn't happy with are the fact that if you have a yoke mount, as indicated here, with a bearing on the south side and a bearing on the north side, you can see from the length of the tube, it cannot look at the North Pole, because if you look towards the north, you're just looking at the north bearing of the yoke mounting. And in fact, the exclusion region of the Hooker was 30 degrees. So there was a disk 60 degrees in diameter that could not be accessed at any time. So you've got a reasonable chunk of the sky. You could, in principle, go down to the southern horizon, but you're excluded from 30 degrees of the North Pole. Maybe something interesting might happen there. Maybe if there is going to be a supernova, it would go off 25 degrees away from the pole, and you would not be able to look at it at all. The second limitation of the Hooker telescope was the mirror. The mirror was made of plate glass, and plate glass will expand or contract quite a lot if the temperature varies. And there's no way to guarantee that the temperature at which you hold the telescope is the temperature that it's going to be at night. It might drop in temperature by 5 degrees in between the day temperature and the night temperature. Even if you're trying to keep the telescope temperature constant, you can't necessarily predict what the nighttime temperature is going to be, and therefore you don't know how cold or warm you need to make the telescope. And it would take hours for the plate glass mirror to come to equilibrium with the nighttime air. In some cases, it might take 12 hours to come into equilibrium, and you would only get the mirror in the correct shape towards the end of the night, shortly before sunrise. Many, many hours were lost simply sitting around waiting for the mirror to either warm up or cool down, depending on what its temperature was compared to the night air. And being plate glass, a small change in temperature of 1 degree would make a huge difference to the actual expansion of the mirror, and hence the shape of the mirror, and stars were malformed until everything had come into equilibrium. So let's deal with these one at a time. Yoke mount. How do you get around the problems of the yoke mount, even though you're dealing with a telescope which is going to be substantially heavier? So you can't really use a German mount. You can't really use a fork mount. After a little bit of toing and froing, they came up with the iconic solution of the horseshoe mount. So you can see that in principle, the tube can point to any horizon in the south or the east or the west, but most importantly, you're not excluded from the pole, because if you want to, you can simply bring the telescope up into the middle of the horseshoe, which defines the polar axis. So you see that the North Pole axis is not a single point. The North Pole axis is distributed over the outside edge of the horseshoe, and there are oil bearings here to support the weight of the north side of the yoke mount. So it is extremely rigid. It can take a huge load, many hundreds of tons, and you're not restricted in terms of how close to the pole you can go. So that was a great solution to that particular problem, and it's become the iconic appearance of the Hale telescope. This is what the mirror looks like if you look at it from the side. The 100-inch Hooker telescope was made by pouring glass from 3 individual pots of molten glass into the mold. And you can see the 3 pourings because it's clear that part of that glass started to solidify before the next pot was poured in, etc. So you've got a lot of structure in there, and you notice a huge number of air bubbles that couldn't be removed. It was essentially impossible to anneal these air bubbles out. So you have a huge internal structure, which means that as you warm it up or cool it down, not only does it expand and contract quite a lot, it expands and contracts irregularly because of the internal structure and because of the air bubbles. Air expands at a different rate to glass expands as the temperature changes, and therefore this silvered surface at the top there would become completely unreliable compared to the nominal shape it should be, the nominal parabola. That shape was completely unreliable for focusing stars until it had come into equilibrium. So if you're going to make a bigger mirror, twice the diameter, 4 times the area, is it going to be 8 times the mass? But the Hooker mirror was 5 tons of glass. Are you going to scale that up so that you've got 40 tons of glass? That is going to be a problem. So they looked at what was possible. Scaling it up was not viable. They had to find a way, if they were going to double the diameter, of saving weight, so you didn't have 40 tons of glass at the back end of the telescope. They decided that they'd have to use something novel, and they decided low expansion glass. This was already around. The Corning Glass Works were already making low expansion glass. Why? For cookware, custard jugs. Thousands of custard jugs were being made by Corning that had very little expansion as a function of temperature, which is why they can go in and out of a hot oven without cracking. So Hale approached Corning Glass Works and said, apart from custard jugs, would you like a bit of a challenge? Would you like to build something larger? So they started to think about low expansion glass. They took a little deviation through quartz. Quartz would be a fantastic material to use, but they didn't have the technology to make mirrors out of quartz. It's possible to do it now. It wasn't possible in the 1920s and 1930s. So to avoid having a mirror 8 times heavier, they had to figure out how they were going to deal with the glass pouring to make a lightweight mirror that was still just as strong and held its shape. Even if the temperature went up and down, it had to hold the shape that the mirror was ground to. So a standard way of making a mirror is you have a large pancake mold and you fill it with molten glass. You take glass, you heat it up until it's molten, you pour the glass into the mold, and you end up with a pancake that's nominally flat on the top and flat on the bottom. Once it's sat there for a while and annealed, you then basically cool it slowly down to room temperature. It might be at 1,500 degrees or so when the glass is poured, but then you have to bring it down to room temperature. With the Hooker telescope, you could do that quite happily in a few months. After annealing the plate glass, you could bring it down to room temperature. But if the glass was 8 times the mass and only 4 times the surface area, you have a problem with how heat is going to escape from that glass. And it was calculated that if you simply scale up the Hooker mirror, in order to make sure the glass was fully annealed, and all of the imperfections, all of the stresses removed, and in order to make sure that you took it down very, very slowly from its molten state to room temperature, it was calculated that you'd have to take it from molten to room temperature over a time period of approximately 10 years. If you tried to cool it down any faster, you'd introduce stresses into the glass which would make it unusable. So they had to find a way around this ridiculously long anneal time. So the normal way of doing it is you make a slab of glass, and after it's cooled down, which might take months or years, you then grind the surface to the shape you want. You grind it to a sphere, and then you take that sphere to a parabola, and then you coat it with metal, and then you've got your reflecting surface, a thin layer of aluminium, as silver tends to tarnish too quickly. So that's the way it was done for the Hlco. What was the alternative for the 200-inch to make sure you didn't have to wait 10 years to anneal the glass? They decided to remove a lot of glass, but to maintain the rigidity. And they did that by filling the mold with fire bricks, cores they're called. And then you pour the glass in, and the glass flows around these fire bricks effectively, which, once the thing has been cooled to room temperature, the fire bricks can be removed. So the glass flows around them, and then when you cool the glass down, you remove the bricks, and then the front surface is ground to the right shape, the sphere and then a parabola, and then coated with metal in the usual way. So what you end up with is a mirror that in principle is much larger in diameter, but hasn't got that much more glass, because you've effectively generated a whole load of ribs on the back, because there's a large number of voids where the glass flowed around the cores, and the cores have now been removed. So you end up with a mirror which is larger but stronger and light relative to the scaled up size of the Hlco telescope. And that's what it looks like. That's what the mold looks like, a large pancake mold, but full of these cores. You can see the actual cores themselves are quite large compared to the relatively narrow ribs of glass that will form when the glass flows around all of those cores. A big plug in the middle. It's going to be a Cassegrain telescope, so we need a plug in the middle to make a hole to allow the light through for the Cassegrain focus. So that's what the molds looked like. And Corning tried to make one of these mirrors. This is the Corning Glass Works as of the mid-1930s. I appreciate you can't see the detail. This is just to give you an idea of what's going on. There's a large annealing oven where the glass is actually poured. This is where the mold sits, and that's where the glass is going to be poured. The glass is melted in a large tank over there. About 60 or so tons of glass were melted in a tank, and about 20 to 25 tons were actually ladled from the tank into the mold and poured into the mold over a period of about a day by a team of people with what looks like a large ice cream scoop, which is actually a ladle that will take between 100 and 200 kilograms of molten glass. Let's see that in action. So this is courtesy of the Corning Glass Works. A whole load of people get on the end of the ladle, and then everybody jumps on it to try and counterbalance, and then out comes 100 kilograms of molten glass. Water is continually sprayed on the ladles to make sure the ladles don't melt. The last thing you want is a molten ladle. So there's the scoop going in upside down like an ice cream scoop. It's turned around, and you scoop up from the tank 100 or 200 kilograms of glass. And there it is. You scrape off any excess, and you keep spraying water onto the ladle to stop the ladle melting. You then take the ladle over to the mold, open a door to the oven, in it goes, and then you literally just pour it out. You can't really see the mold at the bottom there, but that's the glass being poured into the mold. Then it comes out, and any excess is tipped into a wheelbarrow, and the wheelbarrow is taken back to the tank for recycling. So none of it gets wasted. Fantastic. And that process of taking 100 kilograms from the tank into the mold, 100 kilograms at a time, that would be repeated hundreds of times during the day to try and get 20 tons of glass into the mold. So there's the team of people. The guy at the front calls the shots. He determines where that glass gets poured into the mold to try and make sure that the mold is filled nice and evenly. You can see the weight is taken by this overhead rail system. They are there to try and guide it into the right position. There's another picture of the ladle being taken into the mold and turned upside down under the supervision of, this is clearly a supervisor because he's wearing a hat. So, but this is quite nice because you can see the actual structure of the oven itself, the annealing oven, full of bricks, full of fire bricks. That's how you build an oven. You build it out of bricks, and then you have heaters to keep it at 1,500 or so Celsius. But there was a problem. In 1934, when they tried to make the mirror, they hadn't appreciated that it is possible for some of these bricks on the inside wall to get dislodged because of the extreme heat, and some of them fell and plonked into the glass. Also, the mold itself, those fire bricks, are effectively cemented down, but some of them got loose. And fire bricks are lighter than glass, so any fire brick that is released will pop to the surface and float. So you end up with a glass mirror with stuff sticking out the top. Not good. Once it's cooled down, you end up with a mirror with huge gouges in it once you've taken the bricks or the fire bricks out. It was thought, can we rescue that? Is there any way that we could put this back in an oven and anneal it again and get that glass to flatten off? Or is it possible simply, because we're going to grind an awful lot of material out of this mirror, is it possible to grind it to the point where those gouges don't matter? And the answer is no. The gouges were just too deep, and some of them went down to the fire brick, and there was no way that they figured they could rescue this. So they learned from their mistakes. They made sure that the oven didn't have any loose bricks that could possibly come in. They made absolutely sure that for mold number 2, all the fire bricks were bolted down as securely as they possibly could be so that they could have a second crack at it. The public were invited to the first one. The public were not invited to the second pouring sometime later, where they figured, now that we've learned from our mistakes, let's see if we can get it right. So the first one is now in a museum. But the second pouring in 1935 worked. So the first one was a mess. The problems were fixed for the second one, and the second one was then checked by looking at whether or not, we're now looking at the back of the mirror. These are the ribs that we form from the various fire bricks that are in there. They simply looked to see whether there were any signs of stresses after this mirror had been cooled down over about a year, not 10 years, but 1 year of cooling. Are there any signs of stresses in any of the ribs in the back of the glass? They couldn't find any. That's what's being done here, a test. And they declared that basically the second pouring was a success. This is just a publicity photo from Corning Glass, just to remind people that the Cassegrain aperture in the center of the mirror is large enough for a man to squat inside, about 1 meter or so in diameter. It again reminds you of the scale of this mirror. For publicity purposes, they produce leaflets like that saying, we've just built a mirror. It's an eye that sees the distance. Why people thought of telescopes as being eyes is not altogether obvious, but that's the way they got these messages over to the public. The eye that sees an awful long distance. What is that distance? Well, it was thought that once the 200-inch telescope is up and running, it ought to be able to see 1 billion light years. So they simply converted 1 billion light years into miles, and that's what you get. So that's what this telescope ought to be able to do. So they put it into the Corning publicity saying, look, we are the people that have built the largest mirror in the world, the eye that sees that many miles. They had all sorts of other problems. They had problems with the annealing ovens. They had a flood. The annealing ovens have to be powered for a year because you've got to take the temperature down gradually. The annealing ovens were powered from a transformer, and the local river flooded, and the water came very close to the transformers. Their solution was to take the transformers offline and move them 1 floor up as quickly as possible and then reconnect. So rather than try and simply stop the water hitting the transformers, they moved the transformers up 1 level. And they also had a small earthquake as well whilst they were trying to deal with that. They had an awful lot of problems, but they dealt with it, and the mirror was declared perfect. Now we just have to get it from one side of the country to the other, because the Corning Glass Works are on one coast, Caltech on the other. So they shipped the mirror over. There's the mirror on a strap. Let's hope the strap is strong enough. There's 20, 25 tons of mirror. Again, you can see it's translucent because there's not that many centimeters outside of the ribbed structure that we can see on the back. The circles here are effectively where the mirror support structures are going to be. Once it was in Caltech, they took it into the optical shop and said, right, we now need to simply grind a spherical shape and then grind a parabolic shape on top of that. It took approximately 21 men, 11 years to do it. It should have been a little bit shorter, but there was a specific reason why it was more than just a few years, which I'll come to in due course. but 21 men were on the team to actually do the polishing. That's roughly what it looks like, a large horizontal turntable, and then you have the polishing tool, various people. It seems that one is doing the work and at least two are watching from this particular view. Maybe that's how it works there. I can't remember exactly what speed it rotated at, but you can imagine a slow rotation of the mirror and then the polishing tool moves backwards and forwards, etc. And when they think they're getting close to the right shape, they test it. But in this optical shop, they can't really test it with the mirror flat on its back, so they tilt it until the mirror is vertical. And now you can appreciate the absolute need for having a good mirror support. If you want to figure a mirror when it's horizontal, but you want to test it when it's vertical, you have to be absolutely sure that you're supporting the mirror so that there is no distortion of that shape at all, even though gravity has now turned through 90 degrees as far as the mirror is concerned. And that's one of the geniuses of the way this thing was designed. I, again, haven't got time to talk about the details, but the mirror support systems were designed as passive systems that would counteract any gravitational pull in any direction and provide exactly the right reaction force to keep the mirror supported such that the distortion of the mirror surface was effectively minimal. So this guy is not doing the vacuuming, he's just trying to pick up any tiny bits of metal which might be floating around inside the optical shop to make sure that you don't get any scratches that you don't need. What I find amazing about old pictures like this is various individuals with pipes. I can't believe they were actually smoking, but I presume they still need a pipe in their mouth because it's just an affectation, perhaps. So in order to make sure the shape was right, they basically had a knife edge test. So there's a knife edge test being carried out at the other end of the lab, mirror at one end of the lab, knife edge test at the other. If we see what's going on with that gentleman, we can see that, yeah, it's pretty much the same as any amateur would use if they were making their own mirror. In parallel with the mirror being figured to the right shape, they started working on the observatory itself. You could argue that's relatively straightforward because all you need, remember, you're sitting on a granite block of a few trillion tons. You just have to make sure that your foundations are well anchored to the granite. So you dig a few piles and then you start constructing. Once you've made the walls high enough, you're ready for the track on which the dome is going to rotate. The dome will end up being about 1,000 tons or so. So you want the rails on which the dome runs to be nice and smooth such that Hale said, when this dome moves, I don't want to be able to tell through the telescope that the dome is moving. So the engineer said, well, how smooth would you like the rails to be then? Hale said, the nearest thousandth of an inch should do over the size of the observatory. So that's what they tried to do, to make it as smooth as possible so that when the dome moved, the telescope was not even aware of the fact that the dome was in motion. So once the track was laid down, they could start building the dome itself, and by 1937, it actually started to look like what we recognize as an observatory. And these images, these drawings by Russell Porter, I'm using these drawings, these charcoal and pencil drawings, as an indication of how the telescope worked rather than take photographs, because these are such beautiful works of art, of which I've got quite a few on the front desk. I invite you to come down afterwards and have a quick look at the drawings themselves, and I'll make PDFs available through Mark after the talk. So these drawings of Russell Porter allows us to get an idea of how everything works. He has this knack of being able to draw something as three-dimensional or a two-dimensional section in cutaway, as well as having these little ghost images telling you when the telescope's over here, that's what it will look like. When the telescope's over there, that's what it's going to look like. So that's the same drawing, just blown up slightly so we can get an idea. Let me just take you through the optics. Let's dim that down so we can see what's going on. There's the mirror. I haven't attempted to show its correct curvature. So prime focus is when light hits the mirror and comes to the observing cage, the so-called prime focus cage, at the other end of the telescope. The Hale telescope, the 200-inch telescope, was the first telescope that was large enough that an astronomer could ride inside behind where the normal secondary focus would be. After this, you didn't need to ride in a telescope. Before this, telescopes weren't large enough to ride in the telescope. So effectively, this is the one and only telescope in which the observer sits inside during the observation. So the prime focus, the light comes up at the F3 focus to where the observer can have a photographic plate, for instance. Alternatively, underneath the observer in the prime focus cage, a mirror can fold down to give you a secondary focus, the Cassegrain focus, in which case the light would hit the primary, then the secondary, and then go through a hole, which I haven't shown in the primary mirror, to the secondary, to the Cassegrain focus behind the main mirror. Doing that has the advantage not only of a much longer focal length, it also means you can put much heavier equipment that you can't possibly fit inside the prime focus cage. And it's been estimated that there would be no real problem with adding up to 1 ton of instrumentation behind the mirror before it became a problem in terms of the balancing of the whole situation. If that is not enough for you, it is possible to put a third mirror at the intersection of the right ascension and the declination axes, in which case light would then hit the primary, then the secondary, then the tertiary mirror, and sent down the hollow polar axis to a point in the so-called Coude room. This is called the Coude focus, simply because that last mirror there gives you a kink, and Coude just means elbow, so it's just the elbow focus. The advantage of that is that that point there does not move, regardless of where the telescope is pointing in declination, regardless of where it's pointing in our angle, that focus does not move. So you can have equipment that's as heavy as you like in this region, and that tends to be where you put spectroscopy instrumentation, as indicated by this little part of the drawing there. The construction of the telescope itself was done by Westinghouse. This gives you an idea of the size of the base ring. This is effectively the ring that holds the mirror cell. These are the people, I assume that's probably all of the people who were involved in the actual construction of the steelwork of the tube and the mount. And it's a nice way of gauging the scale of the whole thing. Various pieces being put together, the one piece of the huge horseshoe and the truss structure of the tube itself. This looks like probably a declination bearing being put together in the bottom right there. When most of the construction was finished at Westinghouse, they had this sort of topping out ceremony. Again, Westinghouse is not in the same place as California, so having built everything to spec, they then effectively dismantled bits of it and shipped it over to California. But because this was a sort of a celebration of the fact that the steelwork was effectively ready, you probably can't recognize, but there's a certain dignitary there on the gantry, a certain Professor Einstein. Einstein was a theorist, but he was still quite interested in things like this because he figured that this telescope would be able to see galaxies that were distant enough that he would be able to test some of his theories. The apocryphal story is that some people were talking to his wife and saying, this 200-inch telescope is going to be fantastic. Once this telescope comes online, we're going to be able to tell how fast the universe is expanding. At which point, Mrs. Einstein said, well, that's not very impressive. My husband can do that on the back of an envelope. So this is an indication of how some of these things were made. Remember, the horseshoe is made effectively of 2 horns and a central piece. This is one of the horns, and you can see inside that there's a lot of ribbed structure to try and make the horn as rigid as possible. The last thing you want in a telescope like this is to have things flexing a large amount. Same for the telescope tube. Inside the horn of the horseshoe, you see very thick plates of metal on the outside there. These 4.5-inch plates of metal were bent in a forge press that delivered something like 12,000 tons. That's not a misprint. 12,000-ton forge press to bend these 4.5-inch steel plates to the right shape. That's the middle no, that's one of the other horn sections. Again, this is probably a publicity shot. After you've built it, there's not much point measuring it, because if it's wrong, there's not much you can do about it. Again, you get an idea of just how thick these outer plates are. And there's all 3 of them put together, the left and right horn and the center horn. That gives you a piece of metal that's something like 170 tons. And in order to get the precision of movement, remember it's the outer surface of the horseshoe that's the bearing surface. That little hook there is going to be removed once they've got it sorted out. So basically, they put this entire structure on a polishing machine and polished this outer edge, milled it and polished it to a precision that would allow you to point the telescope with the precision that was required. So it was manufactured in 3 individual parts, bolted together. The outer surface was then polished. When they think it's ready, they then dismantle it again and ship each of the 3 parts over to California. The horseshoe is the northern end of the yoke axis. The southern end of the yoke is something that looks a bit like a sort of telephone handset, especially if you turn it the other way up, it looks like a telephone handset. There's the south bearing, and these 2 circles at the back and the front, they're the ones that take the circular arms of the yoke. The 2 circular arms you can see there. It's fairly obvious, but it never really hit me until I looked at this image, that the individual arms of the yoke are huge and very big compared to a person. And of course they're hollow. Where else does the declination motor go? Of course the declination motor has to be inside one of these arms. And it hadn't occurred to me that that's the only place it can really be effectively, and also there's some other instrumentation in the middle of the other yoke arm. All of these bits that we've been looking at, the bits of the telescope truss system, the horseshoe, the south yoke, etc., all of them had to come up. Remember that wiggly road up to the top there? That's where they had to go. Hopefully not coming off at any of these hairpin bends. But it took quite a bit, not just a single truck, but if you've got a fairly heavy piece, looks like the part of the horseshoe coming up there. In this case, you have 2 trucks pulling and another truck at the back pushing. So you need 3 trucks and a fair bit of concrete just to make sure those trucks have got their wheels on the ground and have got plenty of traction. And then you take it slowly up the hill and try and get up the 6,000 feet. Notice the name of the company they chose to use? Hazard & Son, yes, okay. But as far as I know, they got everything up there in one piece, as it were, or at least in the right number of pieces in order to get it to the observatory. Once they get it to the observatory floor has got a hatch in it, so each individual piece, I'm sure they did the calculations to make sure that every piece was small enough to go through that particular hatch. So there's the south yoke coming through the observatory, and then effectively everything gets laid out on the observatory floor, and then you have a jigsaw to get it back together again. So there's part of the telescope, part of the south yoke, and there's, I think, the part of the horseshoe coming through the aperture there. So it was a hell of an engineering job to make it, separate it, ship it, and then put it all back together again inside the observatory dome. There it is, partially constructed in 1939. Again, it's difficult sometimes to get the scale until you realize there is actually a man standing there, and then again you're reminded of the scale of the whole project. Again, health and safety doesn't really apply in the 1930s, so people will be clambering all over the superstructure. No harnesses, no hard hats. Okay, this guy is wearing a hat, but it's a fedora rather than a hard hat, but it's a nice little clip indicating, again, the scale. Here we're looking at the prime focus cage, so the mirror would be way down at the bottom there, and the astronomer would be sitting in the prime focus cage at the top for actually doing the observing. When most of it was put together, they wanted to make sure it moved the way they thought it would move. So they, here, I think we've got an engineer. I think it's an engineer because his sleeves are rolled up. So there's an engineer and somebody else looking at the motion of the telescope. So we're looking with the telescope trying to point to the southern horizon. It probably would never point to the southern horizon because A, it's too murky down there, and B, it's San Diego. But they wanted to make sure it did operate the way they thought, so they tried to take the telescope down as far as they could. And everything seemed to be okay. But how do you move a telescope of this sort of size? You need huge worm wheels. This is either the right ascension or the declination. It's labeled as the right ascension, but I think they look identical because they are the same size with the same number of teeth. So the right ascension gear wheel, the right ascension worm wheel, is about 14 tons in its own right. And Hale said, when this telescope is operational, I want to be able to point it to an accuracy of about an arc second. But bear in mind that the horseshoe weighs 170 tons. The yoke in total weighs about 300 tons. The telescope tube and mirror weigh about 125 tons. So the whole telescope weighs about 500 tons. And Hale wanted it to have arc-second pointing accuracy, which means these teeth on these gears have to be exceptionally precise. So in the years they took to make sure the mirror was the right shape, another team was trying to make sure that the teeth on the gear wheels were made to not quite the same precision, but certainly fractions of a thousandth of an inch, basically micron precision. So you can see the teeth flying by as this large gear wheel is slowly rotated. So the grinding and the polishing took quite a few years for both of the right ascension and the declination gear. This, I think, is the grinding based on the shape of the teeth. The shape of the teeth changed. Now that we're into the polishing phase, some years later, the teeth are looking a little bit more rounded. How do you know when you've got everything just right when you're making precision changes? You get a man with a pipe to run his finger over every tooth to make sure it's what you think it is. And the ultimate test, of course, is to have a worm wheel and the worm gear mesh to make sure that you then, by rotating this at a known speed, you can then get the gear wheel to move, hopefully with a precision of arc seconds. It was a big task, it was a big ask, but the ultimate precision was pretty much spot on Hale's specification. What size motor do you need to move a 500-ton telescope, either by slewing or by tracking? What sort of humongous motor do you need? Well, that's one of them, and you can get an idea of the scale. That tells you how big it is. 2 horsepower was enough to slew the entire 425 tons to different parts of the sky. And when it comes to tracking, you didn't even need anything that big. 1/12 of a horsepower was enough to track. It was said that once it was actually set up, floating on its oil bearings, it was calculated that it ought to be possible to just move it by hand. And they checked this by getting it perfectly in balance and then releasing all the locks. And then they put a milk bottle on one side. And yes, the telescope tipped over because of the added weight of the milk bottle. So they got the friction down to a ridiculously low level to the point where they could slew and track with very modest-sized motors. And again, some of these drawings down on the front show some of that detail. Russell Porter was a technical illustrator, if that's the right word, who produced a lot of these pencil and charcoal drawings, some of which I'm going to show here, but rather than dwell on the screen, I invite you to come and have a look here, and I will make them available to you as PDFs so you can really look at the detail. But some of the detail in these is truly phenomenal. There's the large right ascension gear, and here's a computer that was designed, an analog computer that was designed to make sure that when you wanted to point to a particular part of sky, it would even take into account the fact that light is refracted through the atmosphere, and therefore at particular altitudes a star will not appear at quite the same altitude that you would expect due to refraction. In principle, that can all be taken into account via cams and gears as part of the analog computer system. When it came to operation, they found the pointing accuracy was so good, they found they didn't actually need that correction, but it was still part of the design. And there's a 2 horsepower slewing motor, and there's a 1/12 horsepower tracking motor as part of the drive system. So I'm not going to dwell on these. There's the horseshoe, there's part of the south yoke, there's what's going on inside the arms of the yoke, a declination motor driving the declination wheel. That's what it would look like looking into the prime focus cage with an observer in the top there. That's what it would look like. I'm not sure if all observers actually wore suits whilst they were taking their data, but that's what it would look like with an observer sitting at the pedestal of the prime focus if they wanted to put a photographic plate there. And if they didn't want to sit at prime focus, mirrors would fold down below them to give them the Cassegrain or the Coude focus. So we're nearly there. Everybody thinks that the telescope is just about there. We're only months from being finished. The telescope and the mount are complete. All the mechanical structure is there. The mirror has been ground to within a few millionths of an inch of the correct figure. So does that mean it's complete? Well, almost, but it's 1941. Pearl Harbor. Unfortunately, the USA gets dragged into the war, and that means all the machine shops, all the optical shops get re-diverted to the military, and everything gets mothballed effectively. And it's only in 1945 that they bring the mirror back out of mothballs and start to finish off the figuring of the mirror. So that's why there was a delay. That's why it took 11 years, not half that, because unfortunately the Second World War got in the way. Now you notice there is a definite dish shape to the mirror as we see it at an angle. Also you notice that there's quite a few blokes there, but now we have women on the scene, so at least they're starting to realize that women can be useful, perhaps because of the war effort. So the mirror is effectively finished, put on a truck and taken up to the top of the observatory. Again, very carefully. Once it's there, they can have a dedication ceremony. So 1948 was the dedication ceremony. Up to this point, it's been the 200-inch telescope. At this point, it became the Hale telescope. It was dedicated to the memory of Hale, who unfortunately died a few years earlier. So Hale never actually got to see the Hale telescope in operation. It gives you an idea of the scale when you realize that at the dedication ceremony, there's the Hale telescope at the top. The observatory floor had something like 1,000 people sat at the dedication ceremony. That's again a reminder of just how big the observatory is. So in the coming months, they were putting the finishing touches on the mirror. You can only do so much in the laboratory. You really need to test a mirror on a star. So they, without coating the mirror, they just left it uncoated, put the mirror in the telescope, looked at a star, and tried to work out whether or not there was any particular part of the surface of the mirror which wasn't quite right. Are there any high points or low points? Not much you can do with a low point, but if there's a high point, you can you can polish it down and start to remove some of those mountains. So effectively, it was try and work out where the high points are. That's where these little bits of tape are. The mirror then comes out, and the master polisher will then try and take a few millionths of an inch off. And then when they think they've got that right, the mirror goes back in the telescope, look at a star, see if the star looks perfect. If it doesn't, try and work out where the high points are, and you do that back and forth until you declare that the surface of the mirror is perfect, i.e. we cannot make it any better. The last bit that comes off that is probably only 1 or 2 millionths of an inch and will not be a very hard polish. It will be the master polisher getting a little bit of jeweler's rouge on his thumb and just stroking the mirror, and that will be enough to take a few millionths off, and that will be enough, hopefully, to correct, to give you the final perfect figure. They were aiming for something like 1/40th of the wavelength of light. They got it down to somewhere around 15 nanometers by this process, manual process. So operating the 200-inch, we have an observer in the prime focus cage. That was Russell Porter's drawing, a magnification of it. That's what it looks like when somebody is actually sitting in there. And that was a publicity shot of Edwin Hubble sitting in the 200-inch. Edwin Hubble did a lot of his work on galaxies and recession speeds and expansion of the universe using the Hooker telescope, but he was very keen to use the 200-inch because he realized he'd be able to get more distant galaxies with larger redshifts. Anybody working in the prime focus cage was probably very appreciative of the war surplus of flying suits, electrically heated flying suits. If they wore those, they could at least keep reasonably warm on these frighteningly cold winter nights. You couldn't do much about anything else. You still had to exercise a certain amount of bladder control, but at least you were warm for most of the night. This is what it might have been like. We've now gone from a suit to a check shirt for some reason, but this is what it's like. If you want to put a photographic plate into the prime focus, you would take a plate holder and place it in the top of the pedestal, which is where the prime focus is. You would then take your photographic plate and put it into the plate holder. No, that's not the plate. Put it back. Yep, there's the plate. Yeah, you got it. Yeah, so in the box, in the dark, you take the plate out, and then you put the glass plate into the plate holder. Then, that's it, he's got it now. Then you put the back on, and you make sure that the back is securely placed to keep the glass nice and flush. You're then in a position to say, right, we want to make sure the telescope's pointing in the right direction. So there's a small guide scope there, so you can move that guide scope around and put the crosshairs on a convenient star to double check that everything is looking right, that the telescope is pointing in the right direction. Hopefully it should, but just to be on the safe side, they can monitor the crosshairs and make sure the stars are right. You then check you've got your sandwiches for the night, so you just make sure, yeah, sandwiches, check, yeah, okay, everything's all right. So now you can expose the photographic plate, and then you're basically in business. You can check the guide star as often as you like, and if for some reason, for instance, if you're leaning over to one side and producing a slight torque on the entire system, you can make little corrections of the telescope, much like you would in a hand paddle of an amateur telescope. If the light comes down into the Coude room, that's how it looked with the drawing of Russell Porter. This video is taken from the opposite side, so the video looks backwards. So the light is coming down the polar axis of the telescope, and the astronomer is making sure that when he looks up the polar axis, looking at the star or galaxy that's of interest, that everything is lined up. Then that's removed, so the light then hits the grating going into the Coude room. So the astronomer would make sure the light is hitting the grating, and then would move into the Coude room. The light would come through, hit one of these mirrors, then hit the diffraction grating in the top right, and eventually hit a photographic plate holder. So the astronomer would put a photographic plate to record the spectrum of whatever the object is of interest, and then I'm not sure if that's done with a shutter in front of the plate or whether or not this is all done in the dark, but then, because remember, nothing in the Coude room moves, regardless of where the telescope is pointing, as long as the telescope tracks, this will then record the spectrum of the object in question. So that brings us sort of full circle. Now that the telescope is operational in the late 40s, this brings us back to 1951 and the image that I saw some 20 years later when I was now but a lad at school looking through books in the school library. It has been used a lot of times since 1951. We can't claim that it's taken a picture of the Horsehead Nebula and done very little else. It was at the cutting edge of astronomy for the best part of half a century before telescopes got bigger than the Hale telescope. And even after the point where telescopes were made bigger, it was still doing useful things. For instance, here, adaptive optics were tested. Lots of technology was tested on the Hale telescope because it's simply a large mirror telescope. For instance, getting rid of photographic plates and moving over to CCDs. Where was that first done? On the Hale telescope. Then new generations of telescopes come along which only use CCDs. But basically, the Hale telescope paved the way. Adaptive optics, the idea that in principle you can start moving elements, not the main mirror itself, because that's one large chunk of glass, but you can use other elements in the optical train and start to move them in concert with changes in the Earth's atmosphere to try and improve the resolution. And the Hale telescope was one of the first to image individual planets around a star. I can't remember the name of the star, but the star has been removed, revealing at least 2 and probably 3 or maybe 4 planets directly imaged, and the same technology is now being used in other telescopes around the world. The idea of adaptive optics is something that is very impressive when you see this comparison between the Hubble Space Telescope and what the Hale can do. Remember, the Hale was built in the 1930s and the Hubble Space Telescope was built in the 80s and launched in the 90s. But this was 2013, using adaptive optics on the Hale. And it's not the way around you think. The one on the left is the Hale telescope. The one on the right is the Hubble, imaging Ganymede, one of the moons of Jupiter. So if you get adaptive optics right, you can get phenomenal resolution, even better than a space telescope, simply because you're using a 5-meter mirror, not a 2.5-meter mirror. So there's lots of technology that's being used. So I haven't got time to talk about the science that the Hale telescope has been able to deliver, because this talk was about its design and construction. But the Hale telescope has been able to look at star formation. It's been able to look billions of light years. And of course, we now have bigger telescopes with bigger mirrors that can see even further than the Hale. But it has produced amazing advances to our understanding for decades. And even now, 75 75 years later, it is still able to be useful, not because it's the world's largest mirror telescope, but because it's a fantastic test bed to test new technologies. If you want to continue using it, you've got to maintain it, which means every once in a while it needs a new lick of paint. But most importantly, the mirror has to be cleaned. Roughly speaking, every 18 months. California is not the cleanest place in the world compared to the Atacama Desert, and therefore you have to give it a damn good wash. It looks rather bad, it looks terrible, but no, it's okay. It's given a wash and then a bath in acid to remove the metal. And once the metal has been removed, you're now seeing the glass and the cores again, or at least the voids underneath. Then the glass surface is given a damn good wash, such that it is pristinely clean, hopefully exactly the same shape if you haven't been too rough with your washing. It's now exactly the right shape to go back into the illuminizer to get a fresh coating of aluminium to go back into the telescope and be good for another year or year and a half's use. So the Hale telescope, I believe, is still open to the public if you want to go visit. I went there in 1982. I haven't been back since, but it is still a wonderful thing to visit. When I visited, it was in operation. These days, I think you can get a little bit closer rather than being kept at arm's length. Perhaps you can get actually into the observatory itself rather than see everything through a window. It is a spectacular place to visit, both as a wonderful bit of scenery in Palomar Mountain, as well as the technology, as well as the history and the imprint it's had on history. I've been telling you a little bit about Hale. I've been telling you about the site, the mirror, the telescope, and just touched on the idea that it's actually been producing useful things in the last few years as well. I must acknowledge the fact that I've obtained a lot of information from books and in particular from web pages, including the Caltech archives and the Corning Museum of Glass, who've provided all the videos of the glass pouring, etc. I've taken inspiration from various books, including publications of Russell Porter's drawings, from which I've reproduced these ones on the front table, so please come and have a close look. So, to recap, the Hale telescope was the biggest telescope in the world when I was born. It was the biggest telescope in the world for my childhood. It was the biggest telescope in the world for about half my adult life, and it was overtaken only in the 1990s. Correction, end of the 1980s, early 1990s. So it was basically at the cutting edge of astronomy for half a century. There aren't many scientific instruments that can make that claim. And I think that's testament to the scientists who designed it, the astronomers who designed it, the technicians and the engineers who built it, and above all, the person who had the vision to bring it all together. George Ellery Hale. Thank you all very much.